and good evening, Chester. This talk is the bookend to the one I gave in 2018, which was the beginning of everything, where I told you how the universe came to be and how we ended up where we are today. This talk starts from today and looks to the future. And yes, we're going to look at the fate of the Earth, the Sun, and ultimately the galaxy and the rest of the universe as well. The timescale isn't quite 0 to eternity, or if you're a Disney fan, maybe it is, to eternity and beyond. So what we're going to be doing is a little bit of a prologue, and then I'll be looking at the future of the Earth and the solar system, the far future, looking at stars and galaxies, and then we'll be doing some speculative looking to the far, 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 far future and the ultimate fate of the universe. And to try and avoid sending you home too depressed, I'll have a little epilogue at the end and try and brighten things up just a little bit. So back to 2018, when I gave you the story so far, which is how we came to be here, the beginning of everything. So I'm not going to go through the entire talk, but just to remind you that the universe currently, the observable universe, is a sphere approximately 100 billion light years across. And it's expanding. So if we run the clock backwards, we can deduce that everything used to be a lot closer together. And if you think of everything inside that sphere 100 billion light years across, it all used to be a lot closer together, i.e. a few centimeters apart. Now, it takes some imagination to think about the universe, the observable universe, being only the size of a golf ball, but that golf ball expanded. It didn't take too long for the universe to make lots of protons and neutrons, which we now call basically hydrogen and helium. And ever since then, stars have been churning away, turning the elements into heavier elements, turning hydrogen into helium, helium into carbon, ultimately us. So I'm not going to talk about the details. Let's just assume the universe exists as of now. And to try and keep a handle on the timeline of what we're talking about this evening, I've tried to sort of guide you through by having a scale along the top. So this is not years into the future, as you might well figure out. Each box there represents 10 times further into the future. So what we're going to be talking about is, for instance, 10 to the 1, 10 to the 2, 10 to the 3 years into the future from now. 10 to the 4, 10 to the 5, 10 to the 6 years into the future, 1 million years into the future, 7, 8, 9, 1 billion years into the future, and 10, 11, 12, 1 trillion years into the future. So I'll be putting red boxes up throughout most of the next series of slides to help you sort of keep track of where we are. Otherwise, when we're shouting out billions and trillions and millions of years into the future, it can get a bit confusing. So I've got that timeline. And I'm indebted to the work of Adams and Laughlin, who published calculations about, 25 years ago. They published a paper in which they described the timescales on which various astrophysical phenomena are likely to occur. So I'm indebted to them because that allowed me to try and get my slides in the right order. I am not covering one topic at a time. I'm moving through time into the future, and the topic, whether it be the Earth or the Sun or the galaxy, might jump around in order to keep the timescale right. So this is, in a sense, strictly chronological rather than topic-based. So I'm not going to talk about 10 years or 100 years into the future. Let's assume that we don't blow ourselves up. Let's assume that we get climate change under control. After 1,000 years, we know that the Earth is going to slow down more than it has been doing over past decades. We've been watching the Earth slow down for quite a while, and it's been calculated that in 1,000 years, instead of adding a leap second, which is what we do at the moment to keep the Earth's clocks synchronized with the Earth's rotation, we add a leap second every few years. But as the Earth continues to slow down, we're going to need to add a leap second, not every few years, but we're going to need to add leap seconds every few weeks. And I'll come back to this recurring idea of the Earth slowing down as we move forward in time. Now, we know other things are going to happen. We know some stars are going to explode. Some stars are going to go supernova, but we can't really predict when. So it might be that in 10,000 years we have a supernova event, but we can't really predict that. What we can predict is the fact that the Earth's axis continues to precess, which means the direction in which the Earth's axis points in the sky traces out a large circle on the sky once every 26,000 years. We know that, and so we can predict what's going to happen on timescales of order 10,000 years or so. In other words, the circle on the sky that's traced out by the direction in which the Earth's axis is pointing. Currently, the Earth's axis is pointing at Polaris. In another 10,000 years or so, it'll be on the other side of that circle, and the North Star will be Vega. So it'll be a lot easier to find North. Boy Scouts are going to be delighted with the idea that North is the brightest star in the sky. Some people think it already is. They seem to think Polaris should be a lot brighter than it is. But having Vega as the North Star, apart from making Boy Scouts' life easier, are there any consequences of the Earth pointing in the other direction as far as the tilt is concerned? Well, one consequence is, at the moment, if we think about the direction of the Earth's tilt, the Earth is closest to the Sun in January during northern winter, when the Earth's axis is pointing away from the Sun. But when the Earth points in the other direction, that means we're going to be closest to the Sun during northern summer. It's going to exaggerate the seasons. It's going to make the summers a little bit hotter and the winters a little bit colder, because the effect of tilt and the effect of distance from the Sun are going to reinforce each other rather than partially cancel each other out. And there will be variations in the Earth's climate. This one is because of the change of the direction of the tilt of the Earth, and variations in the Earth's climate that are due to either the Earth's spin or the Earth's orbit. They are manifestations of what we call Milankovitch cycles. I'll mention that again, but if you want to know more, go look up that term in Google. We're now looking a little further into the future. We're now 100,000 years into the future. Voyagers, the spacecraft that were launched in the 1970s, will be passing nearby stars. So if you remember, Voyagers were launched in the late 70s. Voyager 1 went past Jupiter and Saturn. Voyager 2 did a gravity assist from Jupiter, Saturn, then went on to look at Uranus and Neptune. So these are actually leaving the solar system. Voyager 1 up here is heading off in the direction of Gliese 445. And so it will be passing close to that star on a time scale somewhere between 10 and 100,000 years, maybe about 30 or 40,000 years. It'll pass through another solar system. And similarly, Voyager 2, heading off in a different direction, will be passing by the star Ross 248. If they're picked up, great. A civilization may well have a look at these and try and work out what the hell they are. But the likelihood is that they're going to pass straight through these solar systems and then spend another 10 or 100,000 years continuing their journey until they pass another solar system, and then another, and then another. Pioneers 10 and 11, there's 10, they were launched earlier, 1972, but they weren't traveling as fast. So the Voyagers are actually going to leave the solar system before the Pioneers leave the solar system. Pioneer 10 is heading off in the direction of Aldebaran. Pioneer 11 is heading off in the direction of the center of the galaxy. Still on a timescale of 100,000 years into the future, we know the Earth's climate is going to change. We see from the historical record that there have been ice ages and so-called interglacial periods, the warm periods in between ice ages. These come and go every 100,000 years or so. And we know that the Earth entered an interglacial period relatively recently. And therefore, the next ice age is due on a timescale of order 100,000 years. We can't, of course, be very precise. But again, this is another manifestation of the so-called Milankovitch cycles, of which I'm not going to say any more, but it's all related to the spin of the Earth and the orbit of the Earth, that these climate changes will take place. Regardless of man-made climate change, there will be climate change for other reasons in the future. Still on a timescale of 100,000 years into the future, the moon is still tugging on the Earth, and the moon is still slowing the Earth down. And after 100,000 years or so, remember at present, leap seconds are added every few years. I said before, they'd be added every few weeks. But we're now getting to the point that the Earth is spinning so slowly that leap seconds would need to be added to the clocks every day. In other words, every day would not be 24 hours long, it would be 24 hours and a second long. The last minute of every day would have to be 61 seconds long to keep the clocks on Earth synchronized with the rotation of the Earth. And that will continue. The moon will continue tugging on the Earth beyond 100,000 years, which we'll see in a few slides' time. So although we cannot tell when supernovae are going to go off, we are fairly sure that on a timescale of 100,000 years or so, almost certainly there will have been another supernova in our galaxy. Candidates, for instance, are the Eta Carina Nebula. This is visible in the southern hemisphere, and it's been sloughing off its outer atmosphere for quite a few years now. The Hubble Space Telescope has been imaging the nebula produced by the outer atmosphere escaping effectively from this particular star. It's a very massive star, and it's a definite candidate to go supernova. We can't tell when, but we think it's on this sort of timescale, somewhere in the next few tens or 100,000 years or so. Betelgeuse is on the same sort of timescale. This looks like a Photoshop, and indeed it is a Photoshop. It's actually a genuine picture of the night sky, photographed above an observatory in Prague. But the photographer here has taken a genuine picture of the night sky, and then he's exaggerated the brightness of Betelgeuse to show what it might look like when Betelgeuse decides to pop its clogs. So, of course, it's going to completely ruin the constellation of Orion there, but I guess we'll put up with that just because of the spectacle of having a supernova, a very bright light in the sky, probably visible during the daylight hours as well. So again, we don't know the time scale, but probably on this sort of time scale. Betelgeuse is a few hundred light years away, and if it decides to go supernova, that's no big deal, because 600 light years is far enough away that we can consider that to be safe. But there are some stars that are going to end their lives where even at a distance of, in this case, 7,000 light years for this particular star called Wolf-Rayet 104, even at that distance, when this star dies, it might be a problem. The radiation burst that results from the death of a Wolf-Rayet star might, in principle, exceed that of a supernova. These stars can have extremely fast rotation systems which produce jets via mechanisms which aren't fully understood just yet. But if we happen to be lined up with one of those jets, in other words, if the jets happen to be pointing in our direction when the star dies, the amount of radiation produced, even at a distance of 7,000 light years, could be a problem. It's been calculated if we happen to be lined up with one of these jets, even at that distance, it could basically end life on Earth. Now, that's unlikely in the sense the alignment has to be perfect. It's much more likely the jet will miss us, and it might graze us, it might miss us completely, but it's something to bear in mind that just because a star is thousands of light years away does not mean it's not a threat to what's going to go on Earth. We're now looking at 1 million years into the future. All stars in the Milky Way are rotating around the center, sometimes in nice, regular, almost circular orbits. Sometimes they're a little more eccentric. But the Earth is going around the Milky Way in a sort of circular orbit, as are lots of stars around it. But they're all orbiting independently, which means every so often, two stars just might happen to get close to each other as they're orbiting around the center of the Milky Way. And it's been calculated, knowing where other stars are and how other stars are moving, thanks to spacecraft like Gaia, which has been mapping the positions and velocities of stars. We know that there's a star not too far away that is actually going to get quite close to the solar system on a time scale of about 1 million years or so. It's called Gliese 710, and Gliese 710 is going to come close to us and then go away again. It's not actually on an orbit like that, it's just the result of the motion of our sun and that particular star. You can see it gets closer than our sun than the Oort cloud. In other words, it's going to go plowing through the Oort cloud as it comes and goes. That's going to produce a huge disruption, and no doubt some of these trillions of icy objects in the Oort cloud are going to get disrupted, and a fair number of them are going to come shooting into the inner solar system. Which means when this star passes by, it's been calculated that there will be comets raining down on Earth, or at least in the vicinity of Earth, lots of them, bright ones, probably at least one a month for the next 1 million years or so. So it's going to be a spectacular comet hunter's dream situation. Bear in mind that in the little time it takes for Gliese 710 to actually come in and out of the Oort cloud, our solar system will actually have 2 suns, just like other planets you know about. Same time scale, 1 million years. Is this supposed to say we're likely to be hit with an asteroid every 1 million years? No, this image is not there for that reason. The image is there, one, so that we can remark, what a stroke of luck, it just missed the visitor center. What are the chances of that, eh? The other point is, no, it's not we would expect one of these every 1 million years. We've actually had lots of impacts of that size, but we've lost the record because these things get weathered. Wind and rain will eventually remove any sign of craters if they are more than perhaps 1 million years old or so. So almost certainly there are lots of other impacts that we simply don't know about because all signs of them have been eroded. And you might say, well, yes, of course, that's going to happen on Earth, but it doesn't happen anywhere else, does it? Because we know the footprints on the moon are going to last forever, don't we? Well, no, there's no weathering, but there are lots of micrometeorites raining down on the surface of the moon. So the moon is getting pulverized with micrometeorites. And on a large enough time scale of order 1 million years, those footprints will disappear, simply because the micrometeorites are effectively dredging up and rearranging the top layers of the lunar regolith. It's been said that not only the footprints will disappear, if you wait a little bit longer, even the lunar lander, even the rover, even all the equipment they've left, if you subject it to enough micrometeorite bombardment for 1 million years or more, all of that will disappear. It will simply disintegrate. So yes, things weather on Earth quite quickly, but don't assume that things out in vacuum don't. They quite definitely weather, but space weather rather than wind and rain. We've now gone forward another factor of 10. We're now at 10 to the 7 years into the future. Remember I said that Pioneer, going a little bit more slowly than Voyager, but still Pioneer will leave the solar system and will probably pass through other solar systems on timescales of 10 to 100,000 years. So why is this here at 10 to the 7 years? Well, that's the time period over which the plaque that is sitting on Pioneer 10 will probably end up being unreadable. So for the first 10 million years of its travel, it's going to pass through hundreds, if not thousands, of solar systems. If it gets caught by a civilization as it goes through, they'll read the plaque, they'll figure out who we are compared to the scale of Pioneer, they'll work out from this pulsar map where we live, and they'll figure out that this spacecraft came from the third rock from the sun. So they can trace it back and find us. If anybody catches this thing after Pioneer has gone through 1,000 solar systems, then the plaque will be so pitted and eroded by traveling through interstellar space. You might think of interstellar space as being a vacuum. Strictly speaking, it isn't. It's full of dust, and effectively the spacecraft is moving through this dust and it's subjecting itself to lots of micrometeorite impacts, and that will simply erode the surface of this particular plaque. It's basically only a piece of aluminium. So unfortunately, the plaque will be unreadable unless somebody picks it up within 10 million years. So fingers crossed they actually get around to doing that. Now we're looking at 10 to the 8 years into the future, and we're asking ourselves about Saturn's rings. But before we ask what's the future of Saturn's rings going to look like, it's probably worth asking the question, where did Saturn's rings come from in the first place? Well, we don't, strictly speaking, know, but it's widely conjectured that one of the moons of Saturn probably disintegrated and produced the rings, and maybe some of the debris material reformed, and it might even have been Mimas that was the original origin of the rings. But when you look at Mimas, you might think to yourself,
that's no moon, it's a space station.
Because it does indeed bear a great resemblance to the Death Star. But simulations have been carried out. If we start with a planet with no rings and one moon, for instance, forget the other moons just for the time being, what if we pulverized that particular moon? Maybe it impacted with another moon. Maybe a comet hit the moon and pulverized the moon. What would happen to the debris? And a simulation carried out by the name on the side there have done that, and they have found what would happen to the debris. Look at the time scale. It only takes days for the pulverized material to form a ring system. You might think that the debris would simply go round as a small cloud and stay as a small cloud, but no, it only takes days or weeks before you end up with what can clearly be described as a ring system. That might have happened a long time ago, but ever since its formation, if this was the genuine formation, the individual particles in the ring system have been interacting with each other, and they're being pulled around by the other moons as well, which means all of the particles in the Saturn's ring system are slowly spiraling inwards, and eventually they rain down onto the surface of Saturn itself. And that is what gave rise to the current ring system that we all know and love. But it is not static, it is continuing. The individual particles are continuing to spiral inwards. We can't necessarily see lots of them changing, but the dynamics can be calculated in a numerical simulation, and we are fairly convinced that all the particles are slowly migrating inwards. And over the next few million years, they'll continue to do so, and by the time we get to 10 to the 8 years in the future, the Saturnian ring system will be no more. So for those of you who love to gaze at Saturn, make sure you do so tonight if you can, because you haven't got that long before it's not going to be there anymore. On the same timescale of 100 million years or so, we like to think of the solar system as being sort of clockwork. We have orreries and we have tellurians, which give us an idea of how the planets move and how the moon goes round the Earth and the Earth goes round the sun. And we build ourselves these little clockwork or motorized models, and we can get fooled into thinking that the solar system is basically clockwork. Well, it's true that if we know where the planets are now, we can work out where they're going to be in 1,000 years' time. We can work out where they were 2,000 years ago, if we're interested to know about the Star of Bethlehem, for instance. But we must remember that on these timescales, 100 million years or so, the solar system is not predictable. It is totally and utterly chaotic. We can't tell where the planets are going to be in a billion years' time. We can't tell where they were a billion years ago. We don't even know if we'll have the same planets. Maybe we'll still have Mercury, Venus, Earth, Mars, Jupiter, Saturn, etc., but maybe not. Maybe some planets will be lost because on this timescale, chaos rules. We sort of know that the simulations tell us that the solar system was probably very different when it formed, and the planets have rearranged themselves, and that's why we have the planets in the order we have them now. But on similar timescales into the future, we can expect other rearrangements. Maybe Jupiter will end up kicking other planets out of the solar system. Who knows? We cannot predict what's going to happen on timescales significantly longer than 10 to the 8 or so years. So orreries are great, but don't be fooled into thinking that they are clockwork forever. Still on a timescale of 100 million years or so, what's happening to the sun? At the moment, the sun, there's you, we are here, in between two spiral arms. We're in a relatively low-density part of the Milky Way. And the Milky Way rotates, or at least the sun goes around the center of the Milky Way, on a timescale of order 10 to the 8, maybe 200, maybe 225 million years or so. But as it does so, we are going to end up going from a region in between two spiral arms. After 100 million years or so, we are going to end up inside one of those spiral arms. In other words, we're going to end up in a denser region of the Milky Way. We're going to have a lot more neighbors than we've got now. At the moment, we've got a star that's about 4 light years away that way, and another star 5 light years away that way. When we're inside a spiral arm of the Milky Way, we're going to have a lot more neighbors within a few light years of us. So more stellar neighbors, what's the consequence of having more stellar neighbors other than having a slightly brighter night sky? Well, there are a number of different consequences. Just as we found that with Gliese 710, if one star gets close, it can disrupt the Oort cloud. If we've got lots of neighbors, presumably we're going to have lots of similar disruptions. If we look through the record and ask ourselves how often have species disappeared from the fossil record, we find that we get spikes, we get extinction events, extinction level events seem to occur, quite a few of them, in the last few 100 million years. And it's by no means regular as clockwork, but it looks like on timescales of order 100 million years or so, we get an extinction level event. The last one was this one, 65 million years ago, the KT boundary, the boundary between the Cretaceous and the Tertiary. That's the one that killed all the dinosaurs and gave us the opportunity of evolving and then giving lectures on the end of everything, some 65 million years later. So it looks like extinction level events are a perfectly natural consequence and might be a result simply of moving into a region of much higher density within the Milky Way, having a lot more neighbors, a lot more chance of neighboring stars disrupting the Oort cloud and sending asteroids our way, some of which are going to be big enough to kill significant numbers of animals on Earth. So this, of course, is an artist's impression, not a prediction as such. So we're likely to get extinction level events on a timescale of 10 to the 8 years. This artist's impression seems to have a large rock that's heading towards Italy, by the looks of it. So bad news for Italy, yes. But of course, if it's a big enough rock, it's going to be bad news for the planet. We are talking literally of global killers. We're talking about extinction level events that will kill large fractions of the entire life biosphere. Species will be exterminated. That is absolutely certain. What we can't really say is whether one of those species will be us. Perhaps we can survive it. We survived the one that killed the dinosaurs. We just happened to be the right size, and the dinosaurs weren't the right size to survive. Maybe we'll be clever enough to figure out how to survive the next extinction level event. Who knows? Still on a timescale of 10 to the 8, because a second consequence of having lots of neighbors, lots of stellar neighbors, because we're now in a spiral arm of the Milky Way, as well as having lots of disruption of the Oort cloud, sending lots of asteroids and comets our way, some of which will collide with Earth. The other possibility is that we find a nearby star go supernova. A supernova within 100 light years of Earth would be a danger to Earth. And indeed, it's been calculated that a supernova within 20 light years of Earth probably would end all life on Earth. At the moment, we don't have any supernova candidates close to us. We're in a relatively sparsely populated region in between spiral arms. We don't have any big supergiants close to us that are going to go supernova. They're all hundreds of light years away. But at this particular point, when we enter the denser part of the Milky Way, we might have lots of neighbors, some of which might be candidates to go supernova. And if they're close enough, that could be a problem. There indeed is a record, if you look in the Earth's sediments, there is a record of this having happened before. Supernova within 100 light years or so are expected to leave a trace element in the Earth's sediments. Supernova produce an isotope called iron-60, and iron-60 doesn't occur naturally. Iron-60 has got a half-life of a few million years. In other words, if a supernova generates this particular isotope called iron-60, we would expect that to disappear millions of years later. It actually goes from iron to cobalt to nickel. But we do find iron-60 in Earth's sediments. So that could only have come from supernova. You don't get iron-60 naturally. It could not have been there when the Earth formed, because any iron-60 that was there when the Earth formed, because of radioactive decay, would have changed into nickel billions of years later. So any iron-60 we find in Earth sediments must have arrived recently, at least within tens of millions or maybe 100 million years or so. It can't be any older than that. So we pretty much know that there have been supernova not that far from the Earth which have generated this particular isotope, which have ended up raining down on the Earth and getting embedded into the Earth's sediments for the fossil record for us, or at least the sedimentary record for us to then examine. So we know it's happened in the past. We expect it will happen again in the future. It's difficult to predict how severe that will be, but it will happen. Still talking 10 to the 8 years into the future. The moon is still tugging on the Earth and slowing the Earth down. Angular momentum is being transferred. Effectively, the Earth is slowing down, and as a consequence, the angular momentum of the moon is increasing, and the moon is getting further away. The size of the moon's orbit is increasing. The moon and the Earth are in tandem. The total angular momentum of that system doesn't change. If the Earth slows down, the moon moves further away. The length of the day is now so long, it's now 24 hours. The idea of adding leap seconds just doesn't cut it anymore. At this point, we'll probably have to throw away the idea of a 24-hour day. Maybe this is the point at which we decimalize and say 25 hours. So the number of quarter hours in a day is now 100. I don't know. We've got plenty of time to figure that out. But because the Earth is slowing down, because the moon is tugging on it, the moon is getting further away, and it won't be long before the distance to the moon is such that we will never get a solar eclipse again. At the moment, the size of the moon's disk is just enough to cover the solar disk, and so we can get a total eclipse of the sun. But if the moon gets further away by another 20, 25, 30% or so, then the moon will never be able to cover the disk of the sun fully. The best we can hope for is an annular eclipse where the moon covers most of the sun, but always leaves either a horseshoe or a complete ring around the sun. So again, for those of you who like eclipse chasing, get your bookings in, because in 10 to the 9 years, it'll never be possible to see a total eclipse of the sun from the Earth's surface. If we think about a second consequence of the moon getting further away from the Earth, not having solar eclipses is, well, it's a bit of a shame, but it doesn't actually have a dramatic effect on the Earth. But at the moment, the moon has a stabilizing influence. In a sense, it keeps the Earth's axis locked at 23 degrees. Well, not strictly locked, but the Earth's axis tilt, historically, we can see that it doesn't seem to have changed much from, let's say, a degree either side of 23.5. 23.5 is the current value. It has changed a little bit. If we look at the cartoon on the left-hand side, that is the Earth's axis changing by about a degree either side of 23.5 degrees. You can see it doesn't have a dramatic effect on the seasons. Having a little bit of a wobble there doesn't have too much of an effect. But if the moon gets further away, the moon finds it difficult to keep the Earth's axis locked at 23.5 degrees. The perturbation from other planets start to come into play, and the Earth's axis can now start to erratically change. So if it's been calculated, if the moon's distance increased by more than about 25%, then it would be possible for the Earth's axis to become totally erratic rather than stay locked at 23.5 degrees. And of course, if the axis is no longer 23.5 degrees, that means seasons are completely all over the place. The Earth's axis could go vertical or even horizontal, and you would start getting the poles become the colder regions become the hot regions become the cold regions. The climate would go absolutely wild, and that is likely to happen on these timescales. Voyager is leaving the solar system, and remember I said it would pass stars in 10 to 100,000 years or so. So why have we got Voyager again at 10 to the 9 years, of 1 billion years into the future? Unlike Pioneer's plaque, Voyager is carrying, both Voyagers are carrying gold disks. Well, actually they're copper, but they're plated in gold. And it has been calculated that the gold disk ought to survive for 1 billion years. That's a little bit tentative, but knowing how stable gold is, and knowing that it's going to be in a vacuum or near vacuum, it's been calculated the gold disk ought to be good for 1 billion years. How come the Pioneer one ended up completely pitted after 10 to the 7 years, but the Voyager disk is good for 100 times longer, for 10 to the 9 years? Well, the gold disk in this case is being protected because the gold disk is behind a cover. So the cover will take all of the impact, and the disk itself should be fine for 1 billion years. The catch is the cover contains the instructions for how to read the disk. So Voyager, again, will pass through solar systems at the rate of 1 every 10 to 100,000 years. So after 1 billion years, Voyager will have passed through tens, if not hundreds, of thousands of solar systems. And if it gets caught in that time by some interested party, they will be able to read this disk and play it and have all these messages from Earth, because they'll be able to read the instructions and know how to play the record. After 1 billion years, if it hasn't yet been found by any civilization, if the first 100,000 solar systems that Voyager goes through do not pick it up and say, what on earth is this that we're looking at, then after 1 billion years, the disk will survive, but the instructions won't. You could argue, well, if they're intelligent enough, they'll be able to figure out how to play it, even if they haven't got the instructions on the cover. Maybe, maybe not. We're still at 1 billion years into the future. The sun hasn't become a red giant yet, but it's on the way. Our sun is middle-aged and it's got plenty of fuel to last quite a long time, but when we're talking about a few billion years into the future, the sun is going to start changing. It won't have run out of fuel, but it's going to start changing on its way towards the red giant phase. Its luminosity is going to increase in billions of years' time. It's been estimated that when it's on its way towards a red giant, its luminosity will increase at the rate of something like 10% for every billion years into the future. That is going to drive the Earth into a greenhouse effect, and the surface temperature of the Earth will become something of order 80 Celsius. A little difficult to survive. You thought 40 Celsius was bad the other year, but no, this is going to be bad. Basically, it'll start to boil the oceans. We'll have to figure out what we do about that in terms of, well, we've got a billion years to decide how we're going to survive that, or whether we have to leave the Earth and find somewhere else to live. The sun is going to be driven towards the red giant phase, and the sun's surface will expand until it's closer to the Earth. And you can imagine, well, that could be a problem. People have calculated what's going to happen to the sun when it goes through a red giant phase. And it's often said that you can calculate how large the sun is going to be, and the sun's radius will end up being comparable to the radius of the Earth's orbit. Yeah. But that doesn't actually mean that the sun is going to be swallowed. It doesn't actually mean the sun will be the Earth will be engulfed by the sun. Because one other thing you have to take into account, well, in fact, there's lots of things, but one of the things you have to take into account is that as the sun expands, it's going to increase the strength of the solar wind. The amount of matter being lost from the surface is going to increase dramatically when the sun goes towards the red giant compared to what it's doing now. So the sun will lose mass, and if the sun loses mass, that means the Earth's orbit is going to expand because the gravitational pull has been weakened. So a little cartoon on the left shows what might happen. The sun will expand, but the Earth will end up moving away from the sun. So as the sun expands, it will indeed at some point engulf the original Earth orbit. That's the calculation of what is likely to happen to the sun based on other red giants we can see. But it might be that by the time the sun gets there, the Earth will have moved away, perhaps to the orbit of Mars or further. There are other things that need to be taken into account, but the bottom line is the jury is out. We're not sure if the Earth will survive the sun going through a red giant phase or not. Let's assume it does for the time being. What's going to happen next? Well, once the sun has gone through its red giant phase, the outer envelope will be sloughed off, and the star itself will be left as a white dwarf. Effectively, what used to be the core of the sun will be left as a white dwarf. No longer any nuclear reactions. A white dwarf is just a hot piece of, well, mainly carbon. So it's thought that it'll be a carbon star. We're not too sure what the pressures are going to be inside, but it might be that the pressure is high enough for the white dwarf to be diamond. So it might be that a white dwarf star is actually a huge diamond with a little bit of carbon around the outside. We know white dwarfs exist. We can't look inside them to tell exactly what's going on. We know there are no nuclear reactions anymore. They are simply called white because they're hot, but they will cool off. Given time, they will cool off. What's going to happen to the Earth once the sun becomes a white dwarf? Well, let's assume the Earth has survived the sun going through the red giant phase and is now a white dwarf. The Earth is going to lose its magnetic field because the Earth's core is going to cool down. The Earth's core at the moment is molten, nothing to do with the heat coming from the sun. The Earth's core is molten because of radioactive heating. There are radioactive elements in the Earth's core that have been there for 4.5 billion years, and the heat from that radioactive decay is keeping the Earth's core liquid, and that's keeping the dynamo going. That's giving us a magnetic field. Eventually, on a timescale of many billions of years, the radioactive decay won't be enough to keep the liquid core of the Earth liquid. The Earth's core will solidify. As soon as it does that, we don't have a dynamo. If we don't have a dynamo, we don't have a magnetic field. And a magnetic field is responsible for keeping a lot of radiation away. Perhaps radiation from the sun won't be important anymore now that it's a white dwarf, but radiation from cosmic rays from the rest of the universe will then start raining down on the Earth because our magnetic field will not be able to keep them at bay. So if we survive the sun going through a red giant, if we can survive the loss of a magnetic field, does that mean our problems are over? Well, except for the fact that the Andromeda Galaxy is going to crash into the Milky Way, yes, on the same sort of timescale, the Andromeda Galaxy is coming our way. On a timescale of 3 or 4 billion years into the future, the Andromeda Galaxy is going to start getting very large. So again, those of you who like your astrophotography, get rid of your telephoto lenses, switch to a wide-angle lens, because this thing is going to get it so close, it's going to fill the sky. By the time the Andromeda Galaxy and the Milky Way start actually going through each other, there is going to be a riot of new star formation. Stars are unlikely to hit each other. It's very unlikely that the sun will hit any star in the Andromeda Galaxy. Gas will interact. There will be interactions between the gas and the dust of one galaxy and the other, but individual stars are probably just going to pass straight through each other because the size of a star compared to the size of a solar system is so tiny. So the two galaxies are going to pass through each other on a timescale of about 4 billion years or so. At first, the two galaxies are going to pass through each other, and then they will sort of rebound and end up settling together into one mega galaxy. To start with, there might be two nuclei. It might be the supermassive black hole of the Milky Way and the supermassive black hole of Andromeda. Maybe they don't merge immediately when the two galaxies themselves merge together. Eventually, those two black holes will become one if we wait long enough. But it's unlikely to be disastrous. It sounds apocalyptic, but it isn't. Compared to the sun going red giant, compared to the Earth losing its magnetic field, this is just a walk in the park. If one galaxy collides with another, it is possible that the sun, because of tidal effects being pulled in different directions, it's possible the sun gets pulled out of the Milky Way. But it's not going to happen overnight. It's going to take millions of years for this to happen. If the sun gets pulled out of the Milky Way, the planets will just go with it. So it's not going to be disastrous for the Earth. It's not going to be disastrous for what's left of the sun, the white dwarf that we will then end up orbiting. So it's not going to be apocalyptic. It's going to be an interesting photographic experience for those who like their astrophotography, but it's not going to be the end of days. We're now going to 10 to the 11 years into the future. At this point, the moon has done everything it can to slow down the Earth. This might look like the Earth and a digestive biscuit. Actually, this is the Earth and the moon photographed from the Deep Space Climate Observatory. In other words, it's one of the few pictures of the Earth and the moon from a distance where you can get a true idea of the scale of the relative scale of the two bodies. Because the moon has been pulling on the Earth now for 10 to the 11 years, it's finally locked them together. In other words, one day is the same as 1 month. The length of time it takes the Earth to rotate once is the same as the length of time it takes the moon to go around the Earth. They are now locked together, tidally locked, so that one side of the Earth always faces the moon. Just like at the moment, one side of the moon always faces the Earth. They will then be locked together as a pair, pretty much like Pluto and Charon now are. So it means that for one particular continent on the Earth, the moon will always be in the sky at the same place. The moon will never rise and never set. The moon will always be at a particular point in the sky. And it means for half the Earth, the moon will never be visible, because only one side of the face of the Earth will ever face the moon. So, again, if you want to photograph the moon, make sure you're in the right hemisphere of the Earth when that locking actually takes place, 10 to the 11 years into the future. We now have got to our red square on the right-hand side, 10 to the 12 years into the future. Things are going to change in the local group, the galaxies around the Milky Way. There's the Milky Way in the center, and if we look at what's going on, the Milky Way is actually surrounded by a large number of satellite galaxies, some of which are quite well known, like the Large and Small Magellanic Cloud, but there are dozens, if not 100 or so, dwarf galaxies scattered all over the place. So as well as the Milky Way merging with the Andromeda Galaxy, the Milky Way is going to merge with M31 and the Triangulum Galaxy and everything else in the local group. The entire group is going to become one mega galaxy. Probably not a spiral, it's probably going to end up as a large elliptical galaxy. So basically, this mega galaxy, whatever it's going to be called, it's not going to be called the Milky Way, it's not going to be called Andromeda, Andrilke, Milkdromeda, whatever its name is, we've got plenty of time to figure that out. Whatever its name is, it's going to be hoovering up everything in the local group of galaxies. What's going on outside the Milky Way and the local group? Well, the universe of the expansion of the universe will continue unabated. At the moment, the expansion of the universe is such that some distant galaxies are actually receding from us beyond the speed of light. For instance, in a separate talk I give, I talk about how it's possible to image with a camera a galaxy that's receding from us at a rate of twice the speed of light. So we know that we can image galaxies even when their expansion velocities, their recession velocities are very high. If you look at the Hubble Ultra Deep Field, for instance, a large number of those galaxies are actually receding from us greater than the speed of light. Some of the closer ones, perhaps not, but many of the more distant galaxies are receding greater than c. And that will get more and more and more difficult to see distant galaxies as we go further and further into the future. The universe, as far as we can tell, will continue to expand, which means there will come a time when even the closest galaxies beyond our own will be so far away we won't be able to image them. In other words, the Hubble Deep Field looks rather wonderful to say if you take a 1 million second exposure, you see thousands of galaxies. But in the future, if you take exactly the same picture with exactly the same technology, you will find that there are no galaxies to be imaged. You will only see the stars that are part of, in this case, the Milky Way. There were 2 stars in that image, everything else was galaxies. And it's sobering to realize that will be the same regardless of your technology. If a civilization arises 10 to the 12 years into the future, if they want to know what the universe is made of and what the universe looks like, if they build themselves a Hubble Space Telescope and do an ultra-deep field, they will see nothing other than the stars in their own galaxy. If they try and work out what the universe is, they will come to the conclusion that the entire universe is everything that they can see in their own galaxy. They will have no inkling that there are actually galaxies out there because the universe will have expanded so much it'll be physically impossible to image them. And it's sobering to realize that we live at a privileged time where we can see those trillions of galaxies. Don't take it as read that that's automatic. In the future, it will not be possible to see all of those galaxies, only the stars within our own galaxy. I told you in the beginning of everything that it took 3 minutes to make all the hydrogen in the universe. Stars are made of hydrogen in the first place, and then they might make helium, which then makes carbon, nitrogen, oxygen, calcium, phosphorus, iron, etc. But it took 3 minutes to make all the hydrogen in the universe, but after 1 trillion years, it started to run out. It is thought that maybe, perhaps hypothetically, maybe you can make a star out of something else other than hydrogen. It's rather tricky. It's more difficult than it sounds, but some people have said that if you look at stellar evolution, as far as we can tell, no stars have ever been made out of anything but hydrogen. But some people have said, well, is it actually physically possible to make stars out of heavier elements, not starting with hydrogen? It's been hypothesized that you might be able to make a star which has nuclear reactions at the core, but a surface temperature so low, it's even lower than, for instance, a red giant, which has a surface temperature of a few thousand Kelvin. Maybe you can make stars which have nuclear reactions at the core, but surface temperatures of only a few hundred Kelvin. It might be possible to make a star with nuclear reactions at the core, but ice in the atmosphere. Frozen stars. And when I say frozen stars, you might have a sort of a Disney version of the frozen stars. That's not what I'm talking about. If that's the picture you've got in your head, let it go, because what I'm talking about is nuclear reactions at the core, ice in the atmosphere. That's somewhat hypothetical and somewhat controversial, but it's an interesting idea. As far as we can tell, it's only really plausible to make stars using hydrogen. Before we go any further, because we're not actually done yet, I know we've reached the end of this line, but I want to spend a few more minutes talking about what happens next. So we need to just briefly think about what's happening regarding the expansion of the universe. Now, there are various models as to how the expansion of the universe works. There's relative size, it doesn't matter what the units are, and there's time. And there's us now. So there's us now at 1. That's simply the size of the universe as we see it at the moment. And the universe used to be smaller. According to the Big Bang Theory, it had 0 size at some point in the past, many billions of years ago. And the different colored lines correspond to how much stuff we can see in the universe. If the universe had a huge amount of mass in it, it doesn't matter what the numbers are, let's just say there's a huge amount of matter in the universe. If that was the case, then as it expanded, gravity would be strong enough, because there's so much matter there, that the expansion would stop, and eventually the orange line here, it would come to a peak, and then it would start contracting again until we ended up coming back to a big crunch in the future. So if the universe is full of lots of matter, we would expect the Big Bang to be followed many billions of years later by a big crunch. But as far as we can tell, that's not the universe in which we live. Our best estimate in terms of, that would be what we call a closed universe. Our best estimate as to how much matter is out there, it's a tricky thing to work out, but when we do the calculations of how much stuff is there in the universe, we think we're on the red curve. We can't be absolutely sure, but a lot of the evidence points to the fact that we're on this top curve. When I was a kid, I think we were on the green curve, but now we've changed minds. So it's not just color blindness, it's understanding how the universe is put together. So if we are on the red curve, then not only is the universe going to expand and continue expanding, notice that the gradient of the line is increasing as well. Not only will the universe continue to expand, the rate of expansion is increasing. It's accelerating. It's just the opposite of what we thought would happen, where we assumed that the universe would slow down a little bit as the expansion continued, because gravity would win. But no, it appears that the red is the best line that we can fit all of our experimental observational data to. So it looks like the universe is going to go on expanding forever. There is no obvious point at which it will come to an end. So in order not to take all the time up until midnight for what I want to say next, we have different numbers in the boxes. Each box is now 1,000,000 times further into the future, not 10. So we're talking not about 1,000,000 years or 1,000,000,000 years or 1,000,000,000,000 years into the future. We're talking about a zillion or a gazillion. I don't know what the actual adjectives are. It makes no sense to talk about descriptions. It's just 10 to the big number, 10 to the big number, 10 to the big number. So where did we get to before we took that little aside? We said that as far as we know, the universe is going to continue expanding. Therefore, if the hydrogen runs out after a few trillion years, stars can live for an awful long time, but they don't live forever. So if the hydrogen runs out, what does that mean? There will come a time when there are no more stars. The age of starlight, as it's called, will come to an end. The amount of hydrogen is finite. Stars don't live forever. There will come a time when there are no more stars. They will not be shining, but what's left of the stuff that used to be stars will continue orbiting around the centers of their galaxies. There will be lots of dead stars, zombies, white dwarfs, neutron stars, black holes, no longer processing hydrogen to make energy to keep the stars shining. Yes, white dwarfs do sound like they're bright, but they're only there because they're hot. They will cool down and they will end up getting dark. With no nuclear reactions to keep them warm, a carbon star, regardless of whether it's carbon or graphite or even diamond, it doesn't really matter what a white dwarf is, it will cool down, and eventually we'll call them black dwarfs. It'll take a while for them to cool down, but there are no nuclear reactions keeping them hot. They are not shining, they are just cooling off. I can make that a little bit brighter, but it doesn't help. It's going to be a very dark object. Some stars will be ejected from the galaxy in much the same way that Jupiter could in principle eject planets from the solar system. Some stars will be ejected from the galaxy, and the rest will be eaten by the supermassive black hole at the center of the galaxy. It's possible to image other galaxies and find that magnetic fields exist around the supermassive black hole at the core. For instance, in a distant galaxy, these have been mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy. That's the infrared telescope in the back of a 747, unfortunately now decommissioned. But that has mapped out the magnetic fields in this particular galaxy, and it's thought that these magnetic fields are what's responsible for effectively funneling the matter into the throat of the black hole itself. So effectively, the supermassive black hole is going to hoover up anything left in the galaxy. We know that atoms at present have got a positive charge in the core and lots of negatively charged electrons going around them. Protons are responsible for the positive charge in the nucleus of every atom in the universe. But maybe protons don't last forever. If protons decay into something else, then atoms will fall apart. All atoms in the universe will fall apart if protons decay. We don't know if they do or not, and we're not sure of the time scale if they do decay. It is thought that it won't be any earlier than 10 to the power 36 years. So it's a long way into the future, but it's a difficult calculation to do. There is no evidence that they do decay, which means that the rate at which they decay is so low, they would probably last for at least this long. But maybe atoms will fall apart on this sort of time scale. If we assume they don't, just for the time being, then atoms will exist for a little longer inside white dwarfs. Remember, there's no atoms in neutron stars, there's just neutrons. There's no atoms in black holes. As far as we know, all matter has been effectively crushed out of existence as far as structure is concerned. So atoms still exist in black dwarfs, but even they won't last forever. They will eventually evaporate, leaving no atoms at all in the universe on this timescale of 10 to the 40-something years. What's going to happen to all of black holes? Well, remember all of the black holes in the center of galaxies. If galaxies merge, the black holes merge, which means black holes are going to grow on this sort of timescale because black holes are simply going to collide with each other, just like the black hole at the center of the Milky Way is going to collide with the black hole at the center of the Andromeda Galaxy. That's going to happen on a cosmic scale, and black holes are going to grow not to millions of solar masses, not to billions of solar masses, but perhaps black holes will grow until they are literally trillions of solar masses in total mass. But even black holes are not eternal. You may think once it's in a black hole, that's it forever, but not according to Stephen Hawking. It cannot be proved, but a lot of people believe Hawking's conjecture that black holes evaporate. They evaporate as long as you wait for a really, really, really long time. Let's remind ourselves this number is getting a ridiculously large number here. So why do black holes evaporate? Let's just do a little one-slide diversion as time is running on here. In quantum mechanics, it's allowed to borrow energy from nothing, and you can use that energy to make a particle and an antiparticle, in other words, a bit of matter and a bit of antimatter, as long as they annihilate and pay back the loan relatively quickly. Energy makes stuff, which annihilates and makes energy again. You can borrow from the bank of nothing, as long as you pay it back relatively quickly, before the universe has had time to realize that you've borrowed it in the first place. So that is as far as we know, a process that is allowed by the laws of physics. What's that got to do with black holes? Well, Hawking tried to calculate what happens if that process occurs just outside a black hole event horizon. So if you imagine that's the event horizon, what if we make something, matter and antimatter, just outside the black hole, and one of them falls in and the other one doesn't? Now one of the particles, or antiparticles, doesn't have a partner to annihilate with, so it can't pay back, which means we've borrowed some energy. Effectively, we've borrowed some energy from the black hole, and it hasn't been paid back. It's just like something has been emitted from the event horizon of a black hole. It hasn't come from the inside. We've made two things. One of them's gone in, and the other one hasn't. But it looks like, as far as the universe is concerned, it looks like something has come out of the black hole. Hawking called this, sorry, he didn't call it Hawking radiation. Everybody else calls it Hawking radiation. And we think that is responsible for why black holes will ultimately evaporate. And it turns out that the radiation increases with decreasing mass. In other words, large black holes don't radiate much. Small black holes radiate quite strongly. That means if a black hole does evaporate, the radiation coming from it is quite weak to start with, but as it gets smaller and smaller and smaller and smaller, the radiation gets faster and faster and faster. There's a sort of avalanche effect, and then the black hole will disappear in a flash of radiation. Even supermassive black holes, even huge supermassive black holes with mass of trillions of solar masses, even they will evaporate as long as you're prepared to wait long enough. The process is so slow, it'll take trillions of times longer than a small stellar mass black hole will take, but it will happen eventually, by the time our red rectangle has got to the extreme end of this line. So have we got to the end of time? Well, we've sort of got to the end of the lecture, so we've almost got to the end of time. We could say that 10 to the power 100, that's a nice round number. That's one Google. No, not that Google. That Google is a misspelling of the actual Google. The actual Google should be an OL on the end. That's 10 to the power 100. And that's not the end, but it has been calculated that after a Google years, all the black holes have evaporated, which means there is no longer any mass, any matter, anywhere in the universe. There's still some radiation. Hawking radiation will have produced some photons which are getting stretched. As the universe continues to expand, these photons of light are getting stretched to longer and longer and longer wavelengths. But the radiation will just float around in this bath that we call the universe, but there will be no matter. Nothing will actually change other than space will continue to expand and the photons of light will continue to be stretched. So if there's no matter anywhere, then nothing happens. And you could argue that the passage of time is determined by watching things move, watching things change. If nothing is happening, then the concept of time becomes pretty meaningless from this point onwards. So it's not, strictly speaking, the end of time, but nothing interesting happens after a Google years. And I don't usually do this, but let's just remind ourselves how silly that number is. One Google is that. It is 10,000 million. I'm not going to read it all out, but you can see that it is a really, really silly number. But it is possible to do calculations of the physics of what happens on these timescales. So end of time? Well, not really, but Woody Allen did say eternity is a very long time, especially towards the end. Another way of thinking of it is to say, well, yes, we are talking about ridiculously long timescales, and the cartoon XKCD had a very good way of summarizing humanity on these timescales. A human is a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process, which involves checking email a lot. That's, as it were, the closest thing to eternity. So let me finish, rather than on a very depressing note, let me try and just make it slightly more upbeat with an epilogue. We live in a golden age. The sun is middle-aged. The sun is stable. The moon is at just the right distance to stabilize the Earth's axis and stabilize the seasons. And as a bonus, it also gives us the possibility of the spectacle of a total eclipse of the sun. Thanks to evolution, we're able to explore and discover, and perhaps more importantly, understand the universe around us. And we can do that by, for instance, building probes which we send out to visit our nearest neighbors. Or if we're clever enough, we can build ourselves telescopes which look out into the universe and tell us that our Milky Way is not alone, but we are in a universe of at least trillions of other galaxies at distances of billions of light years. But humankind could not have existed in the very early universe. We had to have generation after generation after generation of stars processing hydrogen into helium, processing helium into carbon and nitrogen and oxygen and calcium and phosphorus and iron and all the things that we need to make us, us. So we could not have existed in the very early universe, and we've just seen that if we wait long enough, in trillions of years, the universe is going to be really dark and really boring. Which means the best time to exist is, of course, now. Thank you all very much.